Welcome back. So this time we're going to talk a little bit more about chemistry, but we're going to talk specifically about water. And I'm going to introduce you the idea of how we operate for some of the basics of reactions, or how different types of chemicals interact to change. So water itself has 7 unique properties, and we're going to talk about them. The first thing we'll look at is how it is a polar molecule, right? So it means that it has a positive and a negative end. The next thing is that it possesses these polar covalent bonds. That adds to this polarity of having a positive and a negative end, right? So think of it as, you know how the Earth has like a North Pole and a South Pole, just like a magnet has a North Pole and a South Pole? Well, so too, do atoms act in molecules, like for water. So this is like a water molecule right here, some hydrogens. Those are hydrogens, like an upside down bunny rabbit, and here's an oxygen, right? It's going to be more electronegative on this side and more electropositive on the other side. See, it has poles, like the planet. All right. The next thing we'll talk about is cohesion and actually adhesion. So those are ways that because of this polarity, because water has these two different opposite ends, it sticks to stuff, basically. And one of those things it sticks to is itself. And that's really useful for a lot of biological purposes. All right, next thing we'll talk about is the fact that it has a high boiling point and a low density when frozen. Those are also key elements, partially because we don't need water evaporating off if we have higher body temperatures, right? Humans, for example, are similar to extremophilic prokaryotes in that we have a relatively high operating temperature compared to the regular outdoor surface area, right? So that works out really well for us. Also, there's a low density when frozen, which is really important for keeping the planet the right temperature and keeping the water balance just right in our oceans. Another one is evaporative cooling. Now, this is something we use a lot, and I'll talk about this in a bit. The last thing is that it's a really good solvent. So we talked earlier about the formation of ionic bonds, right? And let's face it, living cells are pretty salty on the inside. It means that we have to dissolve certain types of molecules. So it's a good thing we've got water around to help us do that. All right, let's look at water. It's kind of a neat lecture to be giving right now because it's like flash flooding outside. There's some water there for you. So you might hear a couple of thunder rolls. Anyway, oh, there's one now. All right, so let's talk about this water. Okay, we've got a lot of it on the surface of our planet, thankfully, and we're made out of it too. So here's what I was talking about earlier when we talked about this idea of polar covalent. So, hold on, let's get my pen going. There it is. So here's a water molecule right here. And earlier, I drew it with having kind of similar to a planet, right? So there's a North Pole and a South Pole. And you can imagine it as being something similar to a, there it is, a negative end and a positive end. Well, that's how water is all designed, except for water has two kind of ish positive ends. So water really looks like this. There's a negative on one side and another positive on this side. So one of the neat things about this polarity is that it allows it to interact like magnets and get sticky with some of these other molecules of water, right? They form these hydrogen bonds. Oops, sorry, that was supposed to be like an underline moment, not a move the slide moment. Okay, there you go. Hydrogen bonds. Hydrogen bonds essentially act the same way as that big pull that magnets have, the stickiness of magnets. And when you get enough water molecules together, they tend to stick together. So there you go. Properties of polar covalent bonds. So now that I talked a little bit about what something like a polar bond is, let's talk about what a nonpolar is, right? This is really important sometimes to know the opposite. So a nonpolar is an important idea too. So this is an example of a nonpolar molecule. It's methane, right? So methane's kind of interesting because it also has a larger central element, which is a carbon. It also has hydrogens, right, in different places, 4 in this case. But because it can have these 4 bonds, it's we consider it to be a more balanced molecule. It means that there's more equal sharing of the electrons between all of these hydrogens and the carbon. So you don't really have the electrons hanging out like on one side or another side because it's stable in the way that it's built. It means that you also don't have charges. It means that there's no sides where there's a negative or a positive. And that's why methane is very different from something that's polar, like water. Water is going to stick together because it can form these hydrogen bonds, whereas methane is not really going to do that so much. So it's less sticky, and that's the important thing. It also means that it's not going to do things like be a really great solvent, which we'll look at in a bit. All right, let's move on to the next idea. All right, another property of water is cohesion and adhesion, okay? In the book we're using, which is the Pearson biology, we use mainly cohesion, but I like to also talk about adhesion because I think it's really important. All right, so the idea of cohesion, whoa, I think the storm got pretty real outside. Sorry for the blinking. Anyway, so co means that it's going to stick to other water molecules, right? So remember when we had oxygen, hydrogen, hydrogens, and they were negative on this side and more positive on this side, right? Well, another water molecule is going to come around, and that positively charged side of the hydrogen is going to want to stick to that negatively charged side of the oxygen. So they're adhesing to each other. It's cohesion, okay? And that's an important property, especially for things like, for trees. Right here, this is the example for evapotranspiration. So for evapotranspiration, here's how it works. Oh, sorry, I'm chewing gum, so it's terrible, right? Anyway, so for evapotranspiration, what happens is the roots of the plants, right down here, are soaking up all kinds of water, right? So they're soaking up all this water. Okay, and how do they do it? Because this is the blood, like the xylem and phloem of the plant is the blood. And it's primarily water-based, obviously. So how do we get all this water down here in the soil to move all the way up through that tree? Well, we use this property of cohesion. So what happens is as we have on the top, we have these branches, right? So the branches, I should do it green, shouldn't I? They're leaves. Because they have leaves on the top. And these leaves can open and close, right? And so it allows for the evaporation of little bits of water through the top of the tree. And that means, since water is sticky to each other, that the water molecules down here are going to want to get pulled all the way up through the tree as the rest of the water molecules exit. That's a neat property, and plants have really exploited that for some cool circulation. Okay. The other idea is adhesion. And the important idea of adhesion is water sticks to other stuff, right? So we learned how water can stick to itself and how, wow, oh, I didn't realize I could do that. Now I gotta get it back. Speaking of sticking to stuff, there it goes. Right, so now we know things like water will stick to itself, and that's really helpful for things like evapotranspiration and other things like maintaining the ecology, right? Rivers and streams would never collect into lakes or oceans if we didn't have these cohesive, right, attaching to itself properties. Well, adhesion is also kind of cool because adhesion is the idea of it sticking to other stuff, right? So water can stick to surfaces that are not water. Things like your skin, right? Or lightning is serious. Wow. Okay. Or to other surfaces, helping in things like cooling or even transferring heat, moisturizing, all kinds of different things. All right. So adhesion, think of like adhesive tape. You're sticking something different to something else. And then cohesion, sticking the same things together. So here's just a cool slide that I thought was a nice representation of how the idea of cohesion operates in the ecosystem, right? So this is cohesion. So water, in this case, is sticking so tightly to itself that's allowing, a small animal that's relatively lightweight, to walk on its surface without pushing all the way down through it. It creates this idea of surface tension, and that holds water in right? So water can specifically stay in a certain place, such as like a lake or stream, or if you overfill your glass a little bit too full of water, it won't spill over the side right away. So now that we talked about surface tension, let's talk about boiling points, okay? So it has a high boiling point. There it is. Now it has a high boiling point. Okay, so it has a high boiling point. And part of the reason is because of that cohesive property. So if water wants to stick together, it's going to take a lot of energy to break up those bonds. Those water molecules are tight. They don't want to let go of each other. And so that allows us to really be able to push that boiling point until it's, literally 100 degrees Celsius, which is 212 degrees Fahrenheit. That's crazy hot. But it also allows us to have variation in the ecosystems on the planet, as well as variation in the organism's ability to exploit different temperature ranges. And that's been really important throughout evolutionary history. Another important one is it has this low density when frozen. All right? Have you ever noticed, like, when you have a cup of ice water, or anything, iced tea, that's what always gets me, is iced tea. You have a nice big glass of iced tea, and you can't wait to drink out some of it, and you get like an iceberg right in your face, right? Ice is floating, but that's kind of weird because when you think about it, when most types of molecules are in their different states, right? So there's gaseous, and then there's liquid, and then solid. They follow this paradigm, right? So gas is less dense. The molecules are spread out further. Liquid, they're more closely put together. And then solid, they're at their most dense, right? So gas weighs lighter, typically for volume area. Liquid is medium, usually weight per volume area. And then solids are usually the heaviest or the most dense per volume area. But in the case of water, it's a little different. Water molecules actually kind of spread out just a little bit and give us a little more space when they're solid. It makes it so it's lighter, so that we get the icebergs in our face, but more important, we have the icebergs in the ocean. Now, if all the water in the ocean, if all the ice in the ocean, all the glaciers, all the icebergs, everything sunk when that water froze and became solid, then what would happen to the planet? Well, it would become an ice ball, basically. So think about it this way. If all the ice on the planet sunk and went down to like the Mariana Trenches and the deepest parts of the ocean, it would cool the temperature of the rest of the oceans. Eventually they'd freeze too. Eventually the planet would probably drop in a significant way, if not freeze over altogether. So it's really important to maintain the stability of our ecosystem, right? We need to have some icebergs. We need to have some glaciers. So, well, that's an important other property of water. So check this guy out. This guy is hot. Look at this poor guy. He's so warm. His shirt even says heat. I love it. Some of my students told me that that's an actual team. I thought it was just kind of a neat thing they put in the textbook. But anyway, so let's get back into this. Okay, so look at this guy. He's playing basketball. It's hot. You're running up and down the court the whole time. You're inside. What are you going to do? How is your body going to get rid of all this heat, right? This heat. Well, humans have this like really cool way of doing it. It's like us and pretty much like horses. That's it. We're like endurance animals. That's what we do. And we're able to use it as a cooling agent, a major cooling agent. Not just to drink, a nice icy, glass of water, but we can use it because it evaporates so readily. And when it evaporates, it literally takes the heat away from the body, right? And that's another property of those polar covalent molecules. So, humans, here's how we do it. Body temperature rises. We're covered in skin, and we've got not so much body hair, but we also are covered in something else. Really highly modified sweat glands. I mean, you can dump a ton of sweat in an hour. It's ridiculous. And as long as you're sweating enough, and as long as that sweat is evaporating fast enough, it will take the heat away from your body, and it prevents you from overheating. Now, not every animal has that. Actually, not many animals have that. It's a really cool thing. And so we use water as a cooling agent, okay? It's really important stuff. The other thing is it's the liquid basis and solvent for everything on the planet. So one of the things you'll probably notice, especially after you've been sweating a lot, is that you're salty. It's just salty, right? And that's partially because some of that sweat that you're pulling off has lots of dissolved items in it, right? In this case, ions in it. Ions. Salts for the most part, right? And that also contributes to the activity of water as it evaporates. Water is an excellent solvent. This is true. So a solvent in this case is going to be a liquid, water, which breaks up a solid or a solute, right? And it dissolves it in. So, well, I'll just show you something. This is probably better than me trying to draw this one. There it is. This is way better. Okay, so let me show you what water does. Water breaks up ions, right? Especially ionic bonds. Here's how it does it. Okay, so remember earlier when we were talking about sodium and chlorine, and how chlorine like stole one of sodium's electrons, but they still hang out because, you know, sodium's like positive and chlorine's like negative. Maybe it's like an opposites attract kind of thing, because that's, you know, how magnets, and that's how different types of molecules and elements work, or ionized elements at least. So that's part of the deal. So as lots of chlorine and lots of sodium go through this ionic exchange, they start to kind of grid together, and they actually form halite crystals, right? Which halite crystals are kind of cubic in shape, okay? So they all like glob together, and they make halite, and that's the crystalline structure, right? Those are supposed to be some of the chlorine and sodiums, I guess. Anyway, let's look at this perfect grid, okay? And everything's fine. Everything's dandy, and it's going to stay that way for as long as it will. But one of the things that usually will break up that pretty quickly is going to be the introduction of water. And here's what water does. Let's see if I can make this big. There it is. Okay. So I want you to notice what's happening. So all of these positive ends of water, where the hydrogens are being attracted to the negative end of this chloride ion, right? There it is. Okay, and then conversely over here, all of the negative ends of those water molecules are being attracted to the positive end of the sodium ion. And that's how they're tearing apart this big halite crystal. There it is. I think that's it. Right? And so that's how they tear it apart. This is one of the things that makes water an excellent solvent. Okay? And it acts on this solute. And after it's, you know, done its job, breaking up all these little sodium chloride ions, it becomes a solution. Okay? So after all the salts dissolve into the water, or what have you, it could be sugar, it could be 100 different things. Well, actually much more than 100 different things. But when it's become ubiquitous throughout the water, evenly distributed, it's really become a more proper solution.
Properties of solutions and reactions.
This is the pH scale. It stands for per hydrogen. Okay, so there's a couple different ways you can calculate acids and bases, but at least for the purposes of our introductory biology class, let's just look at it in this way. Okay, so if you have an acidic solution right down here, right, something close to the number 0, you're going to have a lot of hydrogens, right? Look, there's way more hydrogens than there are any of these negative OH groups, right? There's a few of those. Okay. Conversely, let's look over here, close to 14. Okay? That's a more basic type solution. So let's take a look inside the basic cup. Oh, it's totally flipped now. I got so many more negative OH groups, right? Then we do positive hydrogens. Lots more. So see how that's flipped? All right. A neutral solution is the next thing. Neutral sits right here in the middle, and that's like pure water, That's a little bit not quite exactly perfect, but generally, let's take a look. Okay, so I have 1, 2, 3, 4 hydrogens, and I have 1, 2, 3, 4 negatively charged OH groups. So 4 is equal to 4. So it's balanced, right? Oh, it's like big and small. Where were we? There we are. I think that's us. Okay. So that's how you kind of interpret this pH scale. Now here's something tricky. Don't mess this up. Everybody does. Don't feel bad if you do a few times. You can just get used to it. If somebody says something has a high pH, it's important to think about what that might mean. Higher numbers on the pH scale are more basic. Lower numbers on the pH scale, like 1, are more acidic. Okay? So that's another important thing. Okay, I think you're pretty much ready. Right. So other things that people kind of like think about. So for some reason it's a little bit more intuitive to realize that acids are corrosive. Okay. So they usually work on a molecular structure. They'll tear things apart. Okay. But it doesn't mean that things like basic items such as bleach are safe. Okay. So I use bleach all the time, but I use it safely because there's some things you need to know about it. It's just as corrosive. It's one of the things that makes it so good at disinfection, for example. So have you ever felt bleach? Like gotten it on your hands and then you feel it. Do you remember that feeling? Just think to yourself, what does that feel like? Does it feel greasy? Does it feel a little slimy? No, actually, it does not feel that. What you're feeling are the membranes of your cells actually dissolving. So that's the greasiness. You're just feeling you dissolving. It's a little gross. But, things to keep in mind. Basic doesn't necessarily mean it's safe. It means that it's corrosive in a different way. So, usually we're looking somewhere along neutral. This is right about where we kind of feel like things are a little bit more balanced, right? Because if their charges are just working on themselves, then they're not working on you and your cells. That's the idea, right? So most cells are kind of around this zone right in here. Okay. All right. pH scale. Reactions. So now we know a little bit more about things like water and polar and non-polar molecules. We know about some bond types, right? We know about hydrogen bonds, we know about ionic bonds, and we know about covalent bonds. So let's talk about how molecules become joined together or separate or just change. It's called a reaction because it's reacting. Oh, sorry, I forgot to turn my pen on. There it is. It's reacting to its situation, right? It's usually another molecule with some change in the environment. So things to think about reactions. Let's look at all the parts. Reactants are the molecules you start with, or elements. Products are after you rearrange them, put them through maybe some heat, is the outcome. So think of reactants as like the ingredients. Okay? Now when you see these little arrows, this is the process or the reaction. Here's like the short form for reaction. Look at that. It needs vowels. Anyway, so you start with your reactants, which are like your ingredients for baking a cake. Your reaction would be like cooking it, mixing up the eggs and maybe doing something like putting it in the oven for 30 minutes on 400. I'm not a big baker, but anyway, baking things. So you're adding heat. You're changing the environment. Cooking. Finish that word. And then the last thing would be the products. That's your outcome. So that would be like the cake. Awesome. That's the cake. So that's how a reaction works. The cake still has all the same things in it. What would you say is in that cake? eggs, flour, dairy, gluten, chocolate. Hopefully there's chocolate in there for me. And those are the same ingredients you put in. So you didn't all of a sudden eliminate something, right? You didn't all of a sudden get rid of the eggs or the flour. You just changed them. You also didn't get something new. You didn't put in eggs and flour and milk and butter and get sardines and anchovies, right? So they've just changed their shape. They've changed their form. They've changed their configuration, right? So that's how reaction works. I like to use a baking example because, believe it or not, baking is so much chemistry. So much chemistry. All right. So let's look at another point. Get that all cleaned up. Okay. So let's look at something else. Other things that are important to remember. You put in what you take out. Okay? So here we have 4 hydrogens. Here we have 2 oxygens. We have 1, 2, 3 different molecules. We've cooked them, we've baked them, we've reacted them, and we have an outcome of 2 molecules. Now, did we lose any atoms? Let's check. 1 hydrogen, 2 hydrogens, 3 hydrogens, 4 hydrogens. All right, all the hydrogens showed up. Check. 4. All right. What about the oxygens? 1 oxygen, 2 oxygen, 2 oxygens. Checks out. So that's an important other part, is you don't lose any of the atoms. What you do is you rearrange the way that they're operating together or who they're bonded to. So like one way to look at it is for this reaction we have here's a bond, and here's a double bond. That's a double bond. Okay? And over here we still have the bonds. We still have the atoms, but the bonds are redistributed throughout our atoms, okay? So we have these new molecules. All right, so even though we have 3 molecules over here and 2 molecules over here, we have the same number of atoms, right? And we've just rearranged the way that things are bonded together. Okay, now let's talk about reactions a little bit more deeply. This is for our class, for like intro biology, non-major stuff, right? This is kind of the last bit that I really ask you to understand, and it's very important. Okay, we looked at how we can put in certain ingredients, certain atoms, certain molecules. We looked at how we can react them, right? We cooked them, we baked them. Now let's look at some different outcomes that people usually talk about. Okay, so synthesis, decomposition, and exchange. So synthesis means to build, means to make something. Decomposition means to break something into parts, break it down, right? And exchange means to trade, okay? So we have a couple of different types of reactions. The ones we'll ask you about, so here's a synthesis. We've taken little a, and we've taken little b, and we've made a bigger C. We built something. That's what C is. C is A and B merged together. Now decomposition, we have something larger, made out of a couple of molecules. We've put it through reaction, and now we have broken it up into smaller pieces. It's the opposite of a synthesis. Got it? Last one is exchange. The only thing that's happening here is we're exchanging dance partners. Okay? I don't know, what's another shape? Squiggle. I like squiggle. Okay, so we're just exchanging dance partners. So now, that's it. They're still the same sizes. They're just bonded to different partners. So remember, if you could just identify the synthesis, decomposition, and exchange reactions, you're going to be on the right track. All right, So that's it for properties of water and some of the basics of chemistry and reactions. If you have questions, you know how to reach out to me. All right. Well, happy studying.